Welcome to the video podcast series here at Ontario High School. This is for Chemistry 1, and we are looking at Unit 10, and this is our first podcast, and we're dealing with nuclear chemistry. So welcome, be ready to take some notes, and we'll move on. We want to focus first on radioactive decay products, and for this, our first learning standard, 10-1, is simply this. I can write the name and symbols of the four major radioactive decay particles and compare and contrast their relative penetrating power. The first of the four major radioactive decay products that we're going to look at is called an alpha particle. And I have in parentheses here that it is a helium nucleus. And the reason for that, when you look at its symbol, we can symbolize it either with a mass number 4, atomic number 2, which represents total mass of 4, number of protons being 2 in terms of helium, that's the 42He that you see there, or because it is an alpha particle, you can also have the 4-2 alpha. The 4 represents that there are 2 protons and 2 neutrons in this particle, and the 2 protons, of course, is an atomic number. So it has a 2+ charge. It is a helium nucleus. It does not include the electrons when this is ejected. And the particle that the decay product originates from is simply an unstable nucleus. Now, in terms of penetrating power, the alpha particle has the least penetrating power of the decay particles that we're going to look at today. In fact, it can be stopped by a thick sheet of paper. The second of the four major decay products that we're going to examine is called a beta particle, and parenthetically here, a beta particle is simply an electron. When we look at its symbol and charge, there are 2 symbols that you may see for this, and the kind of weird looking B with the tail there is the Greek letter beta, and you can see that it has a mass of 0. Remember, the electron is so infinitesimally small in mass that we just count it to have 0 mass. And then instead of the atomic number, Z, because there are no protons here, we simply put the charge, which is a 1 negative charge. Now, this can also be written as a 0 negative 1 E, and it just depends on what textbook you're looking at or what worksheet. They are interchangeable. It's very important for you to not be discouraged by the number of different symbols that you see. Just learn them. That's the best way to get through them, is to be familiar with what these different symbols are. Don't be intimidated by them. The particle that decay product originates from, the beta particle is ejected by a neutron in the nucleus, and that's very important for you to remember. When the neutron ejects the electron, it actually changes into a proton, and when we deal with nuclear equations, we'll show you the end result of that. In terms of penetrating power, the smaller size of the beta particle compared to the alpha particle gives it greater penetrating power. So rather than being stopped by a thick sheet of paper, you would need, for instance, a 1/4 inch thick piece of aluminum foil would be able to stop a beta particle. The beta particle does not have as much ionizing potential as an alpha particle, but it is more penetrating. The third of the 4 major decay products that we're going to examine in this class is the positron. And its symbol and charge, if you'll notice, it's the symbol is the same as the electron, except instead of having a 1 negative charge, it has a 1 positive charge. So we still use the Greek letter beta or an E for the symbol, but we have to make sure that we differentiate between the positron and an electron, which is a beta particle in this case, by that charge. If it's a 0 negative 1 E or 0 negative 1 beta, it's a beta particle or an electron. If it's a 0 + 1 beta or 0 + 1 E in the symbol, then it's a positron. It has a 1 positive charge. The particle that the decay product originates from is a proton. And when a proton ejects a positron, the proton then mutates into a neutron. And that's something, again, we'll get more into when we look at balancing nuclear equations. In terms of penetrating power and ionizing power, it's the same as an electron. In fact, it is considered the antiparticle of an electron. The fourth major radioactive decay product that we're going to look at is gamma radiation. And gamma radiation is high frequency electromagnetic energy. And if you're wondering what electromagnetic energy is, light from a light bulb is electromagnetic energy. We call that visible light. X-rays are electromagnetic energy. Infrared and ultraviolet radiation is electromagnetic energy. Gamma radiation is at the high energy end of that. Radio waves are another form of that. So when we look at the gamma radiation, it is not a particle, but the nucleus, an unstable nucleus, can get to a lower state of energy, not only by ejecting certain particles, but they can also get to a lower state of energy by emitting gamma radiation. Okay? And you can see that the symbol and charge for this are unique. That symbol that looks like a little bit of an italicized Y is actually the Greek letter gamma. It has zero mass because it is not a particle. It doesn't even have the mass of like an electron or a positron, so it's got zero mass, and it also has zero charge. It's neutral. The particle that the decay product originates from, meaning gamma radiation, comes from unstable nucleus. And in terms of penetrating power, gamma radiation has the most penetrating power of any of the radioactive decay products. Is very dangerous. In order to stop gamma radiation, you would need to have several inches of a dense material such as lead. So gamma radiation is highly hazardous to health. Want to review just one more time regarding the penetrating power and the ionizing power of these radioactive decay products. In terms of penetrating power, the gamma radiation has the most penetrating power. A beta particle, which is an electron, and a positron have equal amounts of penetrating power, and alpha particle has the least. In terms of ionizing power, and ionizing power means it's the ability of the particle when it strikes something to remove electrons from it and cause it to take on a charge. And so in terms of ionizing power, the alpha particle, which has a 2+ charge, has the greatest amount of ionizing power, and that should make sense. When you compare it to a beta or positron, the beta particle has a 1 negative charge, the positron has a 1 positive charge, so less magnitude of charge with those, so less ionizing power. And the gamma radiation has 0 charge, and so its ionizing power is the least of those particles. We're now ready to look at nuclear equations. Learning Standard 10-2 says this: I can write balanced nuclear equations using the correct symbols for radioactive reactants, decay particles, and products, being sure that the mass and charge of the overall reactions are conserved. Let's take a look at some nuclear equations. So here are some examples. Oftentimes a problem will be presented to you in this way. For instance, uranium-238, which has this symbol. Now, when I give symbols where we show both A and Z, the mass number and the atomic number, I will always give the top number first and the atomic number, which is the bottom number, second. So I'm going to call uranium-238, sometimes I'm just going to call it 238-92 uranium. When it undergoes alpha decay, this is what occurs. We start with 238-92 uranium. The arrow indicates there's going to be a change, that something's going to happen. On the other side of the equation, because I know this is undergoing alpha decay, one of the products will be an alpha particle. And here's where we have the 4,2 alpha symbol for the alpha particle, mass number of 4, atomic number of 2. And then we have to predict what that other product would be. And when we write a nuclear equation, we want to be at nuclear, not nuclear. So I'm working very hard not to say nuclear. But what we want to make sure is that the mass is the same on both sides of the equations, as well as we start with that atomic number of 92, and on the left side of the equation, on the right side of the equation, we also have to add up to 92. So we have our 4,2 alpha, and then our other product is 234,90 thorium, or we could call that thorium-234. Now, the mass is conserved because if you take the mass numbers of thorium and the alpha particle, 234 plus 4, you get 238, which is the same as the uranium. And then the atomic numbers of 2 plus 90 adds up to 92, which is also the same as the uranium. So that's a balanced nuclear equation showing alpha decay of uranium-238. Now let's look at 4019 potassium, also known as potassium-40, and it's going to undergo positron decay. So we first write our radioactive reactant, which is K with a mass number of 40 and an atomic number, which remember is the symbol Z of 19. When we undergo positron decay, we're going to write our arrow for the change, and then we write the symbol for the positron, which is a 0 plus 1 E, or I could use a 0 plus 1 beta, Greek letter beta. Either one is acceptable, and I will use both, and you're welcome to use both as long as you use them correctly. Okay. When we look at the other product, we know that the mass number has to add up to 40. So since the positron has no mass, the mass number for the other product, the argon, has to be 40. And then we also know that the atomic number, which is 19 on the left side of the equation, has to be conserved on the right side. So since it's plus 1 for the positron, for the argon then has to be an atomic number of 18, because 18 plus the plus 1 would equal 19. So the top and bottom numbers that you see in your radioactive reactant have to be conserved. Those numbers have to match what's on the right side or product side of the equation. When we're writing nuclear equations, one of the things that we want to emphasize with these is that when we write Z, which is the atomic number, it represents the number of positive charges, and that charge has to be conserved on both sides of the equations. So as we look at these from the previous slide, the mass and charge is maintained for uranium. 234 plus 4 equals 238. 90 plus 2 is equal to 92. Uranium has 92 protons or positive charges. The alpha particle and thorium nucleus have 2 protons and 90 protons respectively, so the 92 positive charges are maintained. For potassium and argon, the mass numbers remain equal to 40. The sum of 18 and the 1 plus charge from the argon and the positron add to the original 19 positive charges from the potassium. This can be confusing because a positron is not a proton, and you do not want to confuse it with a proton. It is simply the antiparticle of an electron that has a positive charge. And so this is where you want to be careful to make sure those numbers add up, but please don't confuse a positron with a proton. It is not. But the 19 positive charges from the protons on potassium have to be conserved on the right side or the product side of the equation. So the 18 positive charges from the 18 protons of argon added to the 1 plus charge from the positron equal that 19. If you're wondering what happened to the other proton in potassium, it changed into a neutron. And that's chemistry. Let's look at 2 other nuclear equations. 14,6 carbon, or carbon-14, undergoes beta decay. So for our radioactive reactant, or starting material, it's 14,6C, The arrow means that reaction is going to take place and it yields a beta particle. Beta particle is a 0, -1 with the Greek letter beta, or you could use an E there, but we know that it's an electron that's being ejected from the nucleus. And then the other product is a 14,7 nitrogen, or nitrogen 14. Now, the mass is conserved because a beta particle is considered to have no mass. So 14 for the carbon, 14 for the nitrogen. We have the same amount of mass on each side. For the atomic number for carbon represents 6 protons, which have 6 positive charges. There has to be a net value of 6 positive charges on the other side. So on the other side, the 7 positive charges represented by the 7 protons in nitrogen are added to the 1 negative charge from the beta particle. 7 plus -1 is equal to 6. If you're wondering how nitrogen has 7 protons when carbon started out with 6 protons on the other side, it's because one of carbon's neutrons ejected the beta particle or electron, and that neutron then changed into a proton. So that's where nitrogen got its 7th proton from. For gamma radiation, we're going to start with 244-94 plutonium, which also can be called plutonium-244. And when we emit gamma radiation, this is a high energy radiation, but it does not have a mass and it does not have a charge, so it's just 0, 0 gamma. And we're left with 244-94 plutonium on the other side of the equation. The mass is conserved at 244, and the number of positive charges represented by the 94 protons of plutonium stays the same. It still has 94 protons, 94 positive charges. So when the radioactive decay product is simply gamma radiation, the identity of the nuclide, or the nucleus that is emitting gamma radiation, does not change. It maintains its identity. In all other reactions with radioactive decay, the product element is different than the reactant element. There's a change from one element into another. It's time for what we call a your turn problem. And what I'd like you to do is complete the following nuclear equations and identify what X represents in each case. The key to these is to conserve the mass number, which is the top number, and conserve the bottom number, which is the atomic number, which represents the number of positive charges in the reaction. So, good luck to you. I want you to write these down, pause the podcast, write these down, complete it, and when you're ready to check to see how you did, resume the podcast, and I'll show you the answers on the next slide. Welcome back. Let's see how you did. Now, as you look at A, you see that you have 135-53 iodine as your reactant, and as one of your products, you have 135-54 xenon. Well, your mass is conserved there, so whatever X is has to have 0 mass, so you can write that 0 up there. And then the 135-53 iodine, there are 53 protons in iodine, or 53 positive charges, and that has to be conserved. Well, you have 54 positive charges, or 54 protons with the xenon, and for that reason, the particle that you have that has no mass has to have a charge of -1 in order for those 53 positive charges to be conserved. So if it's a 0, -1, it has to be a beta particle, which is the same as an electron, and so this is an example of beta decay. And if you're wondering how xenon got that extra proton, it's because one of iodine's neutrons ejected a beta particle and changed from a neutron to a proton. So that's how that was done. Now in part B, we have 235-92 uranium, and it's going to a 4,2 alpha particle and a 231-90 thorium nucleus. So when we look at this, You had a mass of 235 on the left. You had 4 for the alpha particle. So in order to maintain the mass, whatever x is, has to have a 231 mass. So you would put 231 up there. And then you had 92 positive charges for the 92 protons with the uranium. You know that the alpha particle has 2 protons or 2 positive charges. So in order to maintain that 92, to conserve that, then X has to have 90 protons. Now, when we get the 231 mass and the 90 protons, we can then identify and find the chemical symbol for this element. And we just look on the periodic table to find the element that has 90 protons, an atomic number of 90, and it's thorium. And this is an example of alpha decay. Now the third one, we have an unstable nucleus of carbon, this carbon 11, and we're going to have carbon 11, 11,6 carbon, going to 11,5 boron, okay, plus X, and we needed to identify what X is. We know that the carbon and the boron both had masses of 11, so the mass of the particle that was ejected in this has to be 0. We know that carbon has 6 positive charges for the 6 protons it has, but boron only has 5 protons. So in order to maintain those 6 positive charges from the left side to the right side, we know that X has to have a 1 positive charge, and a 0 mass with a 1 positive charge represents a positron, and so we just write that 0 plus 1 and the Greek letter beta, or you could write that 0 plus 1 with an E. So this was an example of positron decay. How'd you do? Now that you can write balanced nuclear equations, we want to look at nuclear fission and fusion. So Learning Standard 10-3 says this: I can differentiate between nuclear fission and nuclear fusion reactions by examining equations representing each, comparing the energy produced by the reactions, and the advantages and disadvantages of each regarding safety, hazardous byproducts, and practicality. Nuclear fission is a process by which a heavy nucleus, generally these are mass numbers greater than 200, breaks apart to form multiple intermediate-sized nuclei and 1 or more neutrons. Since the larger nucleus is less stable than its products, large amounts of energy are released in fission reactions. Continuing to look at nuclear fission, in a nuclear power plant, an unstable nucleus is bombarded with neutrons, and the symbol for a neutron has a mass of 1, so 1. There are no protons, and it's neutral, so there's 0 charge, and then N represents the neutron, so that's the symbol for a neutron. And a neutron is sent at the nucleus to initiate the reaction, as seen in the sample equation below. So you have 23592 uranium plus a neutron forms 14156 barium plus 9236 krypton plus 3 neutrons, and a neutron again has a mass number of 1 and 0 for the atomic number on that. Please note that these are common products in the above equation, but there are more than 35 different elements that have been observed as fission products of uranium-235. When you look closely at the balanced nuclear equation that represents this fission process, you'll notice that 3 neutrons are produced for the investment of 1 neutron in terms of starting the reaction. So the production of the free neutrons makes it possible to have a self-sustaining fission process as the free neutrons collide with other uranium-235 nuclei. This is referred to as a chain reaction. Some other terms that are helpful in understanding nuclear fission and fusion. The term critical mass, and critical mass is the mass of fissionable material necessary to have at least one of the neutrons cause another reaction and continue the process at a steady rate. So again, you're looking at the equation of the fission reaction below, And out of the 3 neutrons produced, one of them would have to hit another nuclei and cause the reaction that similar to the original reaction from which it was produced. And when that happens at a steady rate, then it is said that you have the critical mass. Okay? If the amount of mass of fissionable material is too small, so that the neutrons can escape without causing another reaction, the mass is considered subcritical. Okay, so that's another term, subcritical, that you want to know. And finally, one more term. If enough mass is present that the reaction escalates, which would mean to speed up rapidly, the heat buildup causes a violent explosion. This situation is referred to as supercritical. So remember that term, supercritical. Nuclear fusion is a process in which 2 or more lighter nuclei combine to form a larger, more stable nucleus. Fusion is a process by which energy is produced in the Sun and similar stars, and the net reaction in the Sun looks like this. You have 4 hydrogens combining to form a 4-2 helium, and then 2 positrons plus an incredible amount of energy. If you are a military history buff and interested in how nuclear energy has been used in weapons, the bomb that was dropped on Hiroshima and the bomb that was dropped on Nagasaki during World War II were what we call fission bombs. That's where the reaction that occurred in the bomb was a fission reaction, and tremendous amounts of energy were put off. The more modern thermonuclear weapons are what are called hydrogen bombs or fusion bombs. And the hydrogen bomb itself has to have a fission reaction to initiate the fusion reaction. So it has an atomic bomb as part of the trigger mechanism in order to produce enough energy to cause the fusion reaction to occur. We have not been able to harness the power of nuclear fusion on Earth for power, which would be of great advantage to us because it takes so much energy to initiate and maintain the reaction. It happens in the stars naturally, but here we have not been able to develop a process where it's usable to us. Well, advantages and disadvantages. As an energy source, fusion has several advantages over fission. The light nuclei are plentiful and easy to obtain, and the end products of fusion are usually light, stable nuclei rather than heavy radioactive ones. But there is one considerable disadvantage. Before light nuclei can be combined, their mutual repulsion must be overcome due to the fact that the positively charged protons of the nuclei repulse each other. Because of this problem, fusion reactors are not yet producing electrical power. Okay, we talked about that a little on the previous slide. The disadvantage of fission reactors in terms of nuclear power are that its byproducts are harmful and have to have special storage, and it's just a much more hazardous way of producing power than what fusion would be if we were able to do it. Well, we've come to the end of podcast 1 of Unit 10 in chemistry, dealing with nuclear chemistry. And though we are at the end, I want to leave you with a thought from J.R.R. Tolkien, writer of the Lord of the Rings book series. Not all who wander are lost. Thanks.